you should have chapter 4 for me. Please send it forward. Just bring them up when you're done. So we're dealing with our deck of cards. We came up with these probabilities on Monday. The chance of getting a red card, 1 in 2. The chance of getting a queen is 1 in 13. What's the chance of getting red and queen?
126.
Why 1 in 26?
There's 2 red queens.
Bingo, there are 2 red queens. But the other way I can look at that is that 1 in 26 also happens to be a half of 13, is a half of 1/13. So I get very convenient reaction. Now, that multiplication fact right there, that's not always guaranteed. So while I circled that, I want to come back to it in a minute. Because I'm using an and here, we call this joint probability. And joint probability depends on other information we have. And that's the critical piece. In this case, chance of being red doesn't have anything to do with chance of being a queen. So that sort of, they don't have anything to do with each other, is an important piece to the way these relate. Let me change the word. Instead of and, what if I do an or? Why 28?
Because you have all the reds, including queens and black.
Aha. I have to think of what else is being done here, right? There are 26 red cards. There are 4 queens, but I've double counted something, haven't I? The 2 red queens are in both piles. I can't do that. So we actually have 2 different ways of thinking of this. I can think of how I count all the cards separately, or I can think of I can count the reds. I can count the queens. But then I will have double counted the red queens, right? So I'll take off the chance of red and queen, our joint probability that we just figured out. So this idea of, I double counted something, so I need to throw it out once. I've included it twice. I need to exclude it, so I really only count it once. That's actually what this result is referred to as, the inclusion-exclusion principle. And in general, I want to add, but I need to make sure that I subtract anything that was counted twice. Think of a subset, right? If all of the things in B were already in A, and I took P of A plus B of B, then I definitely counted all of the B's twice. I counted them once when they were in A, and then I counted them again. I have to take it back out. If our two events have nothing in common, we're going to call those mutually exclusive events. Since the outcomes, the individual simple events inside my compound event, have to be completely separate from one another. Okay, wait a minute. I'm dealing with two sets inside some universe, right? Here's the Venn diagram everybody's used to seeing. When I think of two events as sets inside my universe, I can think of my universal set, my set A, and then I draw another circle, right? Set B. We usually draw them with some sort of overlap. In set terms, if I were to take everything inside both circles, all of it, that's A union B. And that represents our word or. It's a very funny looking U. If I only want the little sliver in the middle, that one little piece is called the intersection. It represents our word and. What does my Venn diagram look like if those two events are mutually exclusive? Yes, Chris.
It'd be just a simple remarkable.
So I want them to have nothing in common at all, right? So not only do I want the two circles, I want them to have no overlap. I'll just draw them apart. So mutually exclusive is going to give me a picture that looks like this. In set terms, we call these disjoint sets. But the other way to think of it is to say that their intersection has nothing in it. A intersect B is empty. And that means that the chance probability of A intersect B must be 0. There are no events in that for me to count. So I'm going to get 0 over whatever, and 0 over anything that isn't 0, that's equal to 0. So let's change the question I asked a little earlier. What is the chance you get a red card and a spade? Because all spades are not red. So red cards, spade cards, ne'er the twain shall meet. On the other hand, if I asked about a red card or a spade, this piece is 0. So if I have mutually exclusive events, then when I do A or B, I just do A plus B. I would subtract the overlap, but there isn't one. Questions? Events are collectively exhausting if they cover the whole sample space. Most of the time, we're just looking at a pair of events. So I want to think of 2 events as being collectively exhausting if they have no leftovers. Everything is covered. Our sample space, right? Our universal set. Now, most of the time, I'm going to want both of these things to be true at the same time. I'm going to want sets that are collectively exhausting and mutually exclusive. But it's not a requirement. They're independent ideas. You can have mutually exclusive, you can have collectively exhausting without each other. The question about the red cards and the spades is clearly not collectively exhausting. What have I left out?
Was it the minus the probability of the red and the spade just there?
Well, but that was 0. I was allowed to leave it out, but I've left something out of my sample space. Somebody say it again. Clubs. There's another suit that I didn't mention at all. So I didn't exhaust my sample space, but they were mutually exclusive. If I divide it into cards whose value is a number and cards whose value is 10 or more, aren't 10s in both piles? But they cover everything. So they're collectively exhausting, but they have an overlap. I haven't created them to be exclusive. Most of the time, I'm going to want that, both, but I can have either one separately. Question. Frequently, I get partial information. The most currently popular card game is Texas Hold'em, right? Poker game where there are cards in the middle that everybody can use. So I can see those cards. But you have two of them that I don't get to look at. So I don't know everything you've got. But I have that partial information. One of the questions is, does having additional information change my result, my probability? This idea is called conditional probability. And we're going to write the chance of A given B. That little vertical bar is red, given. So I'm telling you up front, B has already happened. Does that change what we know about event A? Wait a second. Wait a second. Let me go back to my Venn diagram for a second. If I'm thinking about my Venn diagram, I have two events, A and B. They may or may not be mutually exclusive. I don't know. I haven't said anything about that. A, B. The chance of A would ignore the B circle altogether, wouldn't it? I would pay no attention to the B circle and say, how many things are in A, how many things are in the whole universe? But I'm already giving you the information B has happened. B is true. That changes my universe. Because now I know I'm already in this circle. As soon as I say given B, I'm now really looking just at the B circle. Where's the A thing? Oh, it's in here, isn't it? That's part of A. But what did I call this shape? The intersection. So this piece is A intersect B. So if I've restricted my universe to just this circle, and now I want to know what's the chance of A happening, it's the chance of this happening out of this. I need the size of this divided by the size of that. The chance of A given B is the chance of A and B, I can spell, over the chance of B. Because I've restricted myself to this one circle instead of to the whole universe of set. Instead of the whole sample space. I told you B had already occurred. Remember I said that you couldn't just multiply? Rearrange that. If I write P of A and B all alone, What's on the other side? Oh, that would mean multiplying this piece over to here. So notice it's not the chance of being red, chance of being a queen. The chance of being red, given that I was a queen. This extra piece of information has just showed up. We already said that the chance of having your card turn up as a heart. What's the chance of a heart? Leo.
He's 13 out of 52.
Great.
That's like 25%.
Great. 0.25. Chance of being red, we said was a half.
Because the hearts
20.
and diamonds are red and the other two are black.
Perfect. Now, if I tell you in advance, oops, this is a red card. This is a red card. What's the chance it's a heart? Leo, hang on. Chris? Because now I've restricted myself to the 26 red cards. Half of them are hearts, half of them are diamonds. I'm going to write it following the formula, but I already know all the hearts are red, right? So the chance of being a heart and red is the same as the chance of being a heart. That's 13 out of 52, but the chance of being red is 26 out of 52. The out of 52s cancel. I get 13 out of 26, which is now a half. The chance of having a heart was a quarter. The chance of having a heart given more information is 1/2. Knowing our card is red raised the chance that it's a heart. All right. Bottom of page 163. Last year, 70% of new movies were available as video on demand within 14 days of release. Of those movies, half were released as a pay-per-view as opposed to on streaming. What is the joint probability that a new movie was available as video on demand within 14 days of release for pay-per-view? I want to know joint probability. Joint is what word goes with joint probability? Leo.
It's in union.
Careful.
That other one.
The other one. And, the intersection. So joint means and. That makes sense to me. Join and. I like that. So I want to know the chance of joint probability. What is the chance it was available as video and a TV pay-per-view? I'm asking about an and. So I need these two things. So let's go back and read those sentences again and see if we can figure those out. To do this, I'm going to need some A's and B's, some letters, some variables. The textbook says, all right, 70% of new movies were available as video on demand. Let's define a variable V. It's a video on demand movie. That means that the chance of V is 0.7. Of those movies, 50% were released as TV pay-per-view. Bing, 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 bing. Of those movies, given that my thing is already video on demand, what's the chance that it's TV pay-per-view? I'll call that T. Now I have 50% is the probability of what? It's the probability of T given V. Okay, let me write those things down. And we're trying to find the joint probability, right? We're trying to find the chance that it was video on demand as TV pay-per-view. Video on demand and. Okay. Using my formula up here at the top of the page, P of A and B is P of A given B times P of B. Okay. But here's an interesting English issue. If I say V and T, isn't that the same as saying T and V? So it doesn't matter what order these two letters are in. Over there, it matters a whole hell of a lot. The chance that it's a TV given that it was already video is different than the chance it was video given it was already TV. So that's a very important thing. We'll figure out how to flip those in a minute. Just a sec, Leo. So I'm actually going to say that this is the same as this. Why would I bother to do that? Because then these letters are in the same order as these letters. And that's what I need in my formula. So now I can say this is P of T given V times P of V. And I know those two numbers, multiply them together, and you get
3.35.
poof, 35% chance that you get both. Question.
Does it matter if it's P of V up, so it's the word terminology for it, like P of T given V or P of V given T?
So let's think about our Venn diagram again. And I'm deliberately exaggerating the two pieces, right? P of A given B is that, where B is this big circle and this is A intersection B. But if I do it the other way around, P of B given A, then I'm in the small circle to begin with. I'm looking at that piece. So it's going to make a big difference to what I'm dividing by, right? Dividing by a bigger number, I'm dividing by a smaller number in this case because I've drawn them so out of scale to one another. So yeah, it really does.
But so you, and on there we wrote P of V and T equals P of T and V.
Because the word and is different than the word given, isn't it? Isn't this the same whether I write it as A intersect B or B intersect A?
Yeah.
That's the point. The word and has that switchability. The word given doesn't. Like subtracting, right?
Yeah,
10 minus 5 is very different than 5 minus 10. But adding, I don't care what order I add in, do I? We talk about this as symmetric or asymmetric operations in mathematics, but that's not important here. That's in the discrete class this afternoon. More questions? A lot of times I am not given information as a probability. I'm often given information as odds. Watch the Olympics, watch any sporting event, and then get on DraftKings. You get all sorts of crazy information, don't you? What you also get is odds. Odds are related to probability, they're just expressed differently. If I have the odds in favor of something, well, the odds in favor are defined by the chance of A happening divided by the chance of A not happening. But we'll read it something like this. So let's suppose I have an event that's 4 to 1. The odds are 4 to 1. The number of chances of it happening are 4 yeses for every 1 no, right? There's no probability here yet. What's the chance A happens?
Maybe 4 since 1 is like the things that it's not happening.
But remember that no probability can ever give me a number bigger than 1. The probabilities all have to be between 0 and 1. Oh,
80%.
because for every 4 ways it could happen, there's 1 it couldn't, right? So really, the probability of A is the number of ways A can happen out of the total number of ways something could happen. Chance of A plus chance of not A. By the way, these are odds in favor. So the chance of A happening is the first number. If you write odds against, then the chance of A complement is the first number. So if I want to say the odds in favor of something are 4 to 1, the odds against that something are 1 to 4. Just switch the order of the numbers. I see this having changed in a lot of modern sports betting. There's, edge numbers instead, like plus 150 or minus 200 or something like that. They've changed the way. I still see odds. Odds are given almost exclusively in horse racing, as opposed to the plus or minus system that most modern betting systems use. But Leo, you did exactly this calculation, right?
Yeah.
This piece right here. But as soon as I heard you say the number 4, I went, wait a minute, because every probability must be between 0 and 1.
So it should have been 4/5.
Exactly, I'll point it. More questions? If gaining more information changes my probability, what I can compute, then I say these events are dependent on one another. This is not cause and effect. Absolutely not cause and effect. It's not, I'm just saying, oh, whenever I have B, I will get A. But knowing B changed what I thought about how likely A was to happen. Okay. Telling you the card was red didn't cause it to become a heart. It just changed the probability. Telling you a person smokes doesn't cause them to have lung cancer, it does increase the chances. It changes the probability of the event. So I'm going to use this the other way around, and I'm going to say A and B are independent events if P of A is equal to P of A given B. By the way, I can also measure that using B. P of B is equal to P of B given A. Aha. Hang on a second. Go back to our multiplying formula for the and. Our multiplying formula said P of A and B is the given, the conditional probability times B. But if my events are independent, P of A given B is the same as P of A. If I have independent events, then I can just multiply. Because I can replace the A given B part with P of A. So in the is it red, is it a queen? Being a queen doesn't care whether you're red or not. Being red doesn't care whether you're a queen or not. Those two conditions on my card are independent of one another. Roll a die. Flip a coin. If I tell you the die came up 6, what's the chance this came up tails? There's absolutely nothing the die has to do with the coin, right? Coin doesn't care what the die is doing, the die doesn't care what the coin is doing. You're independent of one another. That's my intuitive definition here. That there's no potential relationship. It is possible that you can have events that are dependent, but the probabilities still work out just right. That I multiply and I get the right number. But that's coincidental. This does not just apply to two things. I could have multiple events. If they're independent, then the chance of all of them happening is just multiply each one together. I have lots of dice. I mean, seriously, I have lots of dice here. So let's suppose that I roll 2 of them. What's the chance that one rolled a 6? Assuming it's a fair die.
Be 1/6.
What's the chance this one rolls a 6?
Be 1/6.
What's the chance they both roll a 6? That's the and, isn't
Be
it?
1/3. 1/12.
Multiply.
Right.
Multiply. 1/6 times 1/6 is 1/36. So when I start playing craps, and I've got 2 dice on the table in front of me, I now have all of the information, all of the odds that I can write down. This annoys the hell out of my in-laws because my son loves doing probability and they play Yahtzee a lot. And that's got 5 dice on it. And he'll just rattle stuff off all the damn time. How did you know that's the chance? Well, it works like this. They're independent dice. By the way, you really want to make people's brains hurt. Play with crazier dice. Those have 20 sides. $120 sides. We can play dice with all sorts of creative. So, what's something where I want to take note of independence? Well, how many of you are using a cloud account right now on your computer? Are you connected to your cloud account? Okay. Your cloud account is someone else's computer, right? That's all a server is. It's another computer in another building that is connected to the internet. So let's suppose I have a computer server and it's got 99% uptime. Now, if you have all of your information on that one computer and you get to access it through your cloud account, then 1% of the time you can't see squat. Uh-oh. That's a problem, isn't it? So Amazon Web Services and all these other internet service cloud account providers store their stuff in multiple servers. If I run a business and I have my stuff on 2 servers instead of just 1, what's the chance I have a crash and can't see my stuff? What's the chance on toast? Say again?
34%.
How'd you get 34?
Because they're 2 like independent, the 2 servers.
The 2 servers are independent, right? So the 2 servers being independent, they both go down. There's a 1% chance the first one goes down, there's a 1% chance the second one goes down. So I'm looking at A and B, that they're both down at the same time. I just took the rule off the page. If they're independent, I multiply, right? So the chance of server 1 being down the chance that the second server is down is 0.01 times 0.01, which is really a lot smaller than 33%. That's 100th of a percent, right? Which means my likelihood of things being okay went from 99% to 0.9999. I may not be able to get my information off of server 1. I may be able to get it off of server 2. Maybe able to get it off of both. But there's a 99.99% chance. If I go to 3 servers, it'll be 9999. It'll be 6 of them. If I go to 4 servers, it's 8 of them. It's a huge option. So if I increase my number of servers, I increase my reliability. My ability to be sure that my information is still available by placing it in multiple places. Until something like what happened to Amazon last year happens and the critical backbone piece goes down and none of you can get to any of the servers. But we're hoping to avoid that. But this same idea of independence and redundance gets me to more useful pieces of information when I need to keep not just information, but processes on play. If I run a manufacturing facility and everything has to go through this one piece of equipment, if that one goes down, I'm so hard. So I need at least 2 of them. I can take one down for repairs while the other one is working. I need to know how reliable they are so I don't get both of them down at the same time. Okay. If I take my probability ideas and make them tabular, I can get something that's far more useful and far closely related to something you should have seen before, a pivot table. Remember pivot tables in Excel? You took this giant pile of data, you correlated rows and columns based on information we've got. I'm going to build a similar idea called a contingency table. So let's suppose that I have 2 pieces of information in my data that I want to know about. For example, I'm going to look at student engagement in the MBA program. And there are 3 different kinds of MBA students, and I'm measuring 3 different levels of engagement. Types of students are full-time, part-time, and those in the executive MBA program. I'll just use those abbreviations. And then I'm going to measure engagement as low, medium, and high. So I've got 9 categories here. We'll put engagement across the top and type over here. And then I'm just going to count how many are in each group. I'm going to make a table of that information. But that is where I will start when Friday from video. Because what's happening Friday? The competition is happening on Friday. So I'm going to pre-record this. I probably will record it and post it tomorrow in the afternoon, but you will definitely have it available to you Friday at class time. So I will not see you Friday. But if you are available, you should come help out at the math competition over in Sicilian between 8:30 in the morning and 1 o'clock. Question, Chris?
What was the last time?
What is the students who are in the executive MBA program? So I've got a full-time standard, I've got the part-time standard, then I've got the accelerated 8-week program thing. So I will see you all on Monday. By the way, what's happening on Monday? Band 1, so I will see you all for that.